This video will walk you through how to solve the problems in the HR diagram lab. First, I strongly recommend that you read through the introduction section. It contains a lot of useful information that will help you to answer many of the questions, as well as just giving you general information on what the HR diagram is and what it shows. Questions 1 through 6 in the exercise section ask us to use the overlays to answer the general questions that follow. The overlays are attached at the very end of the exercise and are labeled figures 6, 7, and 8. So the first question asks, where are the hottest stars found in the HR diagram? Well, the first thing we need to do is to recognize that by hottest, it means that we're looking at the highest temperature star. Now this seems obvious, but we'll use this thought process to establish a pattern for future questions. So at this point, we hope to find one of the overlays that will help us to answer the question. So if we turn to figure 8, we see an overlay that is labeled absolute magnitude versus spectral class, and we see lines of constant temperature. So all we need to do is to place our star at the proper location on the HR diagram. Using the techniques described separately, we'll use this diagram and place some fictitious stars on it. Here we see the star Spica and the star Enif placed on the diagram. We see that Spica is on the 16,000 Kelvin line, meaning its temperature is 16,000 Kelvin. We also see that Enif is labeled and it is placed on the 4,000 Kelvin line. We can then conclude that Spica is hotter than Enif. Note that the x-axis shows us the spectral class of the stars. So we can see that Spica is a B-class star, and Enif, in contrast, is a K-class star. From this, we can immediately see a relationship that O-class stars are hotter than B-class stars. We also then can conclude that B-class stars are hotter than A-class stars, and A-class stars are hotter than M-class stars. A trend in temperature should therefore be evident. Stars on the left-hand side of the diagram are hotter than stars on the right. In order to determine if temperature also has a vertical or top-bottom relationship, we can verify this by adding another star to the diagram. Spica is at the top, so we can add another fictitious star that we'll call Vulcan of the same spectral class near the bottom. Once plotted, we can see that Vulcan is on the same temperature line, so it has the same temperature. Therefore, there is no top-to-bottom relationship. Only the left-right position indicates a difference in temperature. So the correct answer for where are the hottest stars found on the HR diagram? The answer is left. The next question asks, where are the brightest stars found in the HR diagram? It also asks where the dimmest are located. Ideally, we hope to find another one of the overlays. When the question asks for brightness, we know that this is referring to its magnitude. In the introduction of the lab, we see the y-axis labeled as absolute magnitude. Each of the overlays are labeled as such as well. As it turns out, every overlay has this value, so we can pick our favorite one. To make it simple, we'll again use figure 8. Looking at the values on the y or vertical axis, we see that it runs from plus 15 at the bottom to minus 5 near the top. Let's pause for a moment and remember that for magnitudes, the brighter magnitudes are expressed as small or more negative numbers. The larger or more positive numbers are dim. Stars placed near the bottom of the diagram, therefore, are dim, while those at the top are very bright. Let's again go back to figure 5, where we see that Spica and Enif are both at the top of the diagram. Reading off of the absolute magnitude values, we see that both of these stars are nearly the same brightness, to at least within a difference of about 1.5 magnitude. We should again place a fictitious star on the diagram to determine if a left-right relationship also applies. We can put Vulcan near the bottom of the diagram, directly below Spica, and compare. If we read the magnitude off of the axis, we see that Spica and Vulcan are very different in brightness. Therefore, we can conclude that the brightest stars are found at the top of the diagram and the dimmest at the bottom. No left-right relationship exists. The next one asks, where are the largest stars found, and where are the smallest? When the question asks for large and small, we realize this is referring to radius or diameter of the star. Turning to the overlays, we see that Figure 7 shows the relationship by including lines of equal radius, expressed as multiples of the Sun. At the lower left of the diagram, we see a line labeled r equals 0.01. This means that the stars on this line are 1/100th the size of the Sun. Looking at the lines of equal radius, we see a trend of lower left to upper right. That means that both vertical and horizontal components of the size are important. The answer to the questions of where are the largest found, therefore, is the upper right. If we go to a classic HR diagram that shows our different types of stars, we see that the smallest stars in the lower left of the diagram, associated with the smallest lines of equal radius, are labeled as dwarfs, and the stars on the upper part, the upper right, are labeled giants. The labels are consistent with the size of the stars. The next problem asks the location of the most massive stars on the HR diagram and correspondingly the least massive. For this one, we'll turn to Figure 6. Here we see the main sequence line labeled with masses expressed in solar mass, ranging from 0.5 near the bottom of the main sequence to 17 solar masses near the top. This implies a lower right to upper left mass trend. However, this diagram does not tell the whole story. We do generally know that there exists a mass-luminosity relationship for main sequence stars. It only applies to main sequence stars, and it says that brighter stars equal larger mass. We can also look at the evolutionary tracks and see, for low mass stars, the tracks take their location on the HR diagram generally towards the upper right portion, the upper right quadrant. By moving upward, the mass of the star does not get larger, even though the radius does. Also, the evolutionary track for large stars takes a rightward track. Again, moving rightward from the main sequence does not change the mass, though it does change the size. That is, unless the star becomes unstable and blows off mass. So we can generally say that a top-to-bottom relationship exists with more massive stars at the top and lower mass stars at the bottom. The last of the general questions asks where the reddest stars are in the HR diagram, followed by asking where the bluest stars are found. Again, looking at the overlays, we don't find a diagram that specifically shows color. However, we do know that a star's color is directly related to its temperature. An O star, the hottest of the spectral classes, is associated with a blue color. At the cool end, we have M stars that are generally associated with red color. We can conclude then that within the hottest temperatures, being on the left-hand side of the diagram, that region contains the bluest stars. Similarly, the rightmost region has the lowest temperatures and therefore the reddest stars. Some HR diagrams, like this one, very prominently show the color relationship between the different spectral classes of stars. The remainder of the questions all refer to a table of stars provided with the lab. So the first question asks, which star in the table is the hottest? For this question, we know that the temperature and spectral class are related. From hottest to coolest, the spectral classes are, in order, from hot to cold, O, B, A, F, G, K, and M. We see these in the bottom of any HR diagram, with the subtypes 0 through 9, with 0 being the hottest and 9 being the coolest of the same type. We therefore look for the Oest, as I like to refer to it, spectral type to look for the hottest of stars. In this case, Lambda Ori is the only O-class star, so it is the hottest in the table. The next question asks, which star in the table appears the dimmest? Because it includes the word appears, we know that we're looking at an apparent magnitude. We also know that the dimmest stars will have the largest number for its apparent magnitude. So we simply look for the apparent magnitude column, which we are given, and look for the largest number. Wolf 424, with a magnitude of 13.1, is easily the dimmest star in the table. Next, we're asked to identify the star that appears the brightest in the table. We again are looking at apparent magnitude, but this time we want to look for a small number. Spica has the smallest magnitude, so it is our brightest star. For the next one, we return to the HR diagram that asks for the star with the smallest radius. To answer this one, we need to place the stars on the HR diagram as shown in Figure 7, the version that includes the radius or size overlay. We want to look for the one with the highest point in the upper right quadrant. How do we plot the location of the stars? We have the spectral type, referred to on the x-axis, and the luminosity class also is given to us. The luminosity class tells us if the star is in the supergiant, 1A or 1B, the giant category, luminosity class 2 and 3, subgiant, luminosity class 4, or main sequence, luminosity class 5. We also have dwarf stars represented as luminosity class 7. As we look at the table, we notice that we don't find any white dwarf stars listed. We know that for main sequence stars that a relationship exists called the mass-luminosity relationship, which says that dimmer stars equals smaller mass. We find that the star CD 37 degrees 15492, referred hereafter as just CD, is a very dim main sequence star, making it our smallest radius star. Next, we're asked to find the star in the table that is the coolest. For this one, we simply look for the Mist spectral type. Wolf 424 is an M5 star, the rightmost in the table. We are then asked to find the star closest to the Sun in temperature. The Sun is a G2 star. We need, therefore, identify the star that is closest to G2. We find that Epsilon Leo is a G1 star, the closest to G2 of the other stars in the table. The next question asks which star is nearest to us. In the table, we are given parallax angle P of each star. We know that the distance of the star is given by the formula D is equal to 1 over the parallax angle. In other words, the inverse of the parallax angle. That means we can determine the distance by taking the inverse of the provided parallax angle. We have two choices on how to do this. We can either calculate the inverse using our calculators, or we can be a little clever and realize that a smaller parallax angle corresponds to a larger distance. Or the inverse is also true. A larger parallax angle means a smaller distance. The star Epsilon Arri has the largest parallax angle, making it the closest to us. The next question asks for the most distant star. We therefore look for the star with the smallest parallax angle. Alpha Sig has the smallest number, so that makes it the most distant. The next question wants us to identify the star that is closest to the Sun in color. We know that temperature is a predictor of color. We therefore need to identify the star with the nearest temperature. Temperature is not a value listed in the table. Temperature is not a value listed in this table. However, we do remember that spectral type and color are the same. Epsilon Leo is the closest in color with the spectral type of G1. Next, we're asked how many stars are too dim to be seen with the naked eye. We know that the limit of the human eye is a 6. So we look for an apparent magnitude with a value greater than 6. Only 2 stars, CD and Wolf 424, are too dim to be seen. Next, we're asked how many are cooler than the Sun. The Sun is a G2 star. To be cooler, we need to have a spectral type of G3 or more towards the M part of the spectrum. Looking at the spectral types in the table, we find that 8 stars have a spectral type of G3 or cooler. The 5 K stars at the top of the table are listed, as well as CD at M2 and tau set, which is a G8 star. Next, we're asked how many main sequence stars are in the table. We know that the luminosity class of 5, or the letter V, indicates a main sequence star. We therefore only need to count the number of stars with a V in the spectral type. Doing this, we find that there are 6 stars: Epsilon Eridani, CD, Tau Set, Wolf 424, Spica, and Denebula. The next question asks, how many main sequence stars are more massive than the Sun? The specification of main sequence makes this an easier question because we know that the brighter the star in absolute magnitude, the more massive the star. We then need only find main sequence stars with brighter magnitudes than 4.8. Only 2 stars apply, Spica and Denebula. Next, we're asked, which star is intrinsically the brightest? Intrinsically is the key word here. This means how bright the star actually is, referring to absolute magnitude, rather than how bright it appears, or its apparent magnitude. We therefore look for the smallest number for the brightest star. Alpha Sig is our answer, with a magnitude of minus 7.24. We are then asked to identify the highest mass main sequence star. To do this, we look for the highest absolute magnitude of the main sequence stars in the table. We find Spica at a magnitude of minus 2.19.
Is our most negative magnitude.
The last question is a 3-parter. It asks for the mass of a 2 solar mass star. We know the relationship is m to the power 3.5, which gives us a result of 11.3 solar
Luminosity.
Next, we do the same for an object of mass 26. 26 to the 3.5 power is 89,620. The final question in that same group has already been asked in a previous question. The highest mass stars are at the top of the HR diagram, and by this it's only top, there is no left or right component. And this ends how to solve the questions in the HR diagram lab.